Okay, everybody, let's talk about problem R2, which is all about writing equations of rational functions based upon information you're given about the graph. So here's what you need to know, and these are things you learned in Algebra 2 and talked about in pre-cal last year. Whenever you have a rational function, a vertical asymptote can occur from an unremovable excluded value. Now remember, an excluded value is any value that makes the denominator of a rational function equal 0. An unremovable means that the factor that gives you that excluded value will not cancel away. Wholes occur from removable excluded values. So if you have an excluded value and the factor that gives you that cancels when you simplify the fraction, you have a whole at that spot. Horizontal asymptotes occur from end behaviors, and that's what happens when the x is really large or x gets really, really negative. Now you may have learned like certain rules governing horizontal asymptotes last year. We'll talk more about those in this video. And then constant multipliers, multiplying a fraction by a number, doesn't change the excluded values. It doesn't change what causes the graph to have a whole or vertical asymptote. All right, so with those things in mind, let's look at the two examples from the summer work, which is from R2, problems A and B. All right, so we're told in problem A that you have a asymptote at x equals 1 and at y equals 4. So we have a vertical asymptote at x equals 1, because it's a vertical line, and y equals 4 is a horizontal asymptote. Now, because there's a vertical asymptote, we know that there's going to be an uncancelable factor on the bottom of this fraction, and that factor would give us a 0 of x equals 1. So the factor that does that is x minus 1, and that's going to be on the bottom. There won't be anything on top because that would turn it into a whole. Now, that takes care of this piece. Now, if we look at the whole is at 3, 5, which means we have a cancelable factor of x minus 3. So that means we have x minus 3 on top and bottom. That's what makes it a whole rather than a vertical asymptote. It's removable. Now, we have two other pieces of information here that can help us finish this equation. We have a horizontal asymptote at y equals 4, and we have a y value at the whole of x equals 3. Now, it's important to realize that we could have another factor or a constant multiple on top that would affect neither the whole's x value nor the vertical asymptote because it wouldn't change the excluded values. So what I'm going to do is on top say, hey, there could be a factor up here. And that factor will affect what the horizontal asymptote is, which is 4, and what the whole is, the y value at least, which is 5. So that means two things. This factor has two requirements. Number one, it has to give me an end behavior of y equals 4. Now, if I were to look at this, my degree on the bottom is x squared, right? In order for me to get a horizontal asymptote, the degree on the top and the degree on the bottom have to either be the same degree or the one on the top has to be smaller. And if the one on the top is smaller, then the horizontal asymptote is y equals 0. That's one of the things you should have learned last year. Since it's not y equals 0, these degrees have to be the same, which means this factor has to give me some sort of degree that has an x squared in it. That way the degrees are the same. And when the degrees are the same, you divide leading coefficients. So the coefficient on the x squared would have to be a 4, which means inside this factor, we're going to have a 4x to make that work out. That would give me a 4x squared on top and an x squared on the bottom, which when I do my end behavior model would give me y equals 4. Now, this factor could also have a constant added in. So if it has a constant added in, the way I know what that constant could be is I look at the y value of the whole. Now remember with a whole, when you're finding the y value of it, you plug your excluded value, so in this case it's x equals 3, that's what gives where the whole was, into the simplified version of the fraction, which would be 4x plus whatever this thing was over x minus 1. So basically what happens when you cancel out the x minus 3's. That should equal the y value of my whole, which is 5. So with that in mind, I plug in 3 for x, and I cross multiply, and I get that this question mark equals 10 minus 12, which is negative 2, And so the factor that's up here is 4x minus 2, and that's where that answer comes from. So we're going to do part B, so you can see how the process goes again, just to make sure it makes sense. So we'll go a little bit faster, but about with a little less like in-depth explanation, but the same idea. So let's see. First of all, we've got two holes, one at -2, one at +2. So that means that we have an x plus 2 on the bottom and top. That's the excluded value of -2. We have an x minus 2 on bottom and top. That's the excluded value of 2. We have a horizontal asymptote. We don't have one, so we'll deal with that in a second. And a vertical asymptote at x equals 0. So we need a factor on the bottom that doesn't cancel. That gives me 0. So that would be x. Now, it says so we've satisfied the -2, the 2, and the x equals 0. So now we need to satisfy the y values of the holes and the horizontal asymptote piece. Now, horizontal asymptote, remember, degree on top bigger, no horizontal asymptote. Degree on bottom bigger, horizontal asymptote y equals 0. Degree on top and bottom the same, you divide the leading coefficients. So if I look at my current degree on top is x squared. Degree on bottom is x to the third. Right now, that's a horizontal asymptote of 0. But I need this to be bigger because there's no horizontal asymptote. So I need some sort of factor on top that's going to give me a bigger degree than x to the third. Now, there's lots of options. I'm going to choose the simplest one, which would be x squared. And then there could be some other stuff in there as well. So now we turn to the hole. We have two values for the hole, 1 and -1. Let's focus on the 1. So let's see. I want, when x equals -2, I want my simplified version of my fraction, which would be this x squared factor, whatever it is, over x, to equal 1. So if I plug in -2 for x, and there could be like multiple things going on here, let's assume, for now, that it's a full quadratic. And the likelihood of that is not necessarily high, but let's give it a shot. So when I plug in -2 here, I'm going to get 4 minus 2b plus c all over -2 equals 1. Now, that still has b and c in it, right? So what I'm going to do is use the other hole and say the same thing has to equal -1. So now I plug in 2. Oops, sorry, that was a mistake. That's supposed to be 1. -1. There we go. Now I'm going to get these where I can solve for b and c. And then I'm going to use elimination here to solve for b and c. So when I add these two equations together, the b's go away. So I get c is -6. And then if c is -6, then I believe I get b as 0. So that means that this factor up here doesn't have that bx term, but it does have a constant. There you go.